Generation and distribution. I'm Ryan. John Breslin helped me out with this. We can't put our names on it. So this is split up into two parts. There's generation and there's distribution. So the first thing that we're going to look at is how do we do it now, because that seems like a very logical place to start. So the ISS uses photovoltaic cells. It's, as you would think, it's a solar array. So when it's in line with the sun, the solar array will start charging batteries, and then when it's on the night side of the Earth, they can still use the energy, and then it's just a cycle. Now there's two problems with this. There's two reasons why we can't do this. The first one is that these things break really easy, and there's constantly missions to repair them. And the second one is something called the inverse square law, which means that the farther that we get away from the sun, the lower the flux is, because the area increases that we need. The area increases of the photons from the sun. So basically it becomes a feasibility study. So what we did was we split this up into three separate different ways that maybe we can have energy. So the only other way would be to use the radioisotope thermoelectric generation, which is what Voyager uses, but that doesn't last 100 years, so we can't do that. It lasts about 10 from a chart that I saw that I did not put on here. But basically our options are we generate the power ourselves, we recycle the power from the propulsion engine, or we launch the power up with us inside of a battery. So these are the main pros and cons of each, just to have a kind of little chart for everyone. So the generation has the capacity to generate a lot of power, but you're setting up a whole generation system. Just imagine setting up a power plant into space. It's not that easy. And it also is a complex control system using different kinds of pumps and valves and all that kind of stuff, and you need turbines and all of that. Recycling is basically the same as a generation, except it can give us an obscene amount of power, and it doesn't use up as much space or require as much maintenance, because basically what you're doing is you're taking away a whole loop. You're taking away the entire reactor loop because you don't have to worry about it, because you already have the heat. All you have to do is transfer the heat onto the working fluid. But that means that energy considerations for something that is, however, what that was, millions of Kelvin, was it? Millions or billions of Kelvin? So that's obviously hard to transfer heat. And yeah, and cooling it's really, really hard, and you pretty much have to use experimental cooling methods, so something that you didn't have. And the entire nuclear fusion system is pretty much untested. I mean, it's becoming more and more of a thing as I was reading, but there's really nothing to say that we've done that we can do that. And then the third one, which is the one that I don't like that much, but it's kind of like the brute force method. It's because there's no moving parts and it's very easy to assemble, is we just fill a bunch of batteries and we send them up into space. Now that's extremely heavy, and batteries have a tendency to just kind of die out on you. And I think nickel hydrogen metal batteries are the ones that last the longest, and they only last for like 15 years. So you'd have to figure out a way to charge and discharge batteries so crystals will form inside the battery. But yeah, so those are the three. I personally like the second one, but we're gonna go through all three of them. This is the first one. This is the pure power generation. It's also kind of the second. But what you have is you have three loops. First you have the, First you have the loop. This is the reactor fluid. So this is the fluid that's going to take the water, which is the working fluid, and it's going to heat it up to steam. And then you have steam that's going to come out through a nozzle. I'll explain a little bit later. And it's going to come out through a nozzle, and then it goes along turbines. Turbines work by there being an enthalpy difference between one side and the other, so the turbine spins into a generator. We all know that. This isn't anything new. I'm not shooting xenon at pellets. So after you have that steam, you just condense the rest of it. So you have a condenser loop, using probably ammonia, because that's what we use right now. And then you just restart the cycle over and over again. Now the problem is, this one, usually down on Earth, you use fuel. You use coal, you use a nuclear reactor, you use that kind of stuff. So we have a problem with that, and that problem is that it gets used up. So we either have to send a ton of it, which we're already sending a ton of fuel for propulsion, or we have to find another way. So that new way might be photoisomerizing molecules. So this is azobenzene, which I've talked to you guys about before. What it is basically is, in one configuration, it holds a lot more energy than it does in another configuration, and all you have to do to change those configurations is shine a light on it at a certain wavelength. So this, I think, is around the 300 nanometers, and this is around 450. So I know this is hard to read, I kind of just threw this in here, but so here's the thing that I try to figure out. If we shine a certain powered laser at it at a certain frequency, how much would the release of energy be for 1 gallon of this stuff? So we have a milliwatt, a 5-watt laser and a 10-watt laser, I think. And basically what it does is it's shining on the azo to make it one way, and then it's shining on it to make it the other. Now, you usually you think of energy in and energy out, but for the way that azobenzene works is as long as we're near the sun, because the inverse square law doesn't take place right away, but as long as we're near the sun, we just have a constant supply of energy to do this, so we don't have to worry about it. So what we're going to do is create such a surplus of energy that it lasts us throughout the rest of the time. So basically what I did was about per hour per gallon, because it's not exactly in gallons, it's a little, I had to make it a little bit more. You get about 3,412 BTU per hour per gallon. There should be a period there, it's 0.14. So using just an arbitrary 20 megawatts a day, which apparently is not enough, but that gets me to, I have to generate about 68,250,000 BTU a day. So that's 20,000 gallons a day, which brings to 13.9 gallons per minute. That is totally doable. The only problem is these calculations are 100% efficiency. At 30% efficiency, you can do about 4.17 gallons per minute, and after 4.17 gallons per minute, there's no feasible way to do this. It will not last us. At 100% efficiency, this will last us 1,170 years off the surplus energy that we get from the sun. But at 30%, it's not that much. It's like less than 90, I think. So, okay, now we're at the nuclear one. I forgot to put a title. But the biggest problem with the nuclear thing is that we have to figure out a way to cool it off. So what you do is, and my latex on my work computer is really bad, so that's why that looks like that. But basically the way that this works is you have a fluid going in, and you have a gas going in the other way, so it's counterflow. Yeah, I don't think this was just counterflow, but oh yeah, it does. So it's counterflow, and what you do is you have the efficiency, you have the ratio of the capacities between the two, the fluid that's cooling it off, that's taking the heat, because it's not really cooling, it's rejecting heat onto another fluid, and then you have the fluid that's giving the heat. And then you have the number of these coils, and then what you do is, that's how you figure out how many coils you need to get from one temperature to another, using just the simple QMC delta T. So that's pretty simple. I didn't do any kind of calculation with that yet. This comes straight from the ASHRAE manual, so it's pretty solid. Now to the batteries. No matter what, we're using batteries because you have to store power for problems, and you have to store power just in case things go wrong. And it's just better to have the extra in case you need it. I mean, because we can capacitate some systems, so we can't capacitate all of them. So basically, these are the ones that we use now, and they're the nickel hydrogen ones. And they last about 15 years, a little bit longer, and they use 26% potassium hydroxide. This is the paper. I just wanted to make sure that I had the paper that basically shows that this is like the most viable option right now. So what we're gonna have to do is we're gonna have to send up them in kind of like, have them tiered so that some work at some time and then all of a sudden they start catalyzing at another time, so that way to make them go their 15 years. Because there's no kind of, at least electrochemical battery that I was able to find that produces voltage constantly for 100 years. And then the second thing is the distribution, though. This part's the easy part. This is the ISS distribution chart. It's pretty simple. You have the photo array, which is straight DC, and they can set it at a certain voltage, so they can take it in however they want it. And then they use the SSU and then the main serial bus, and basically what that does is it sends it to all these different SPDAs for, it changes it to DC or AC if they need that, it changes the voltage, it's a regulator, it's power supply. So every system gets its own supply of power, so that you don't have to worry about that so much. So we didn't really have to change much, so I just made our own. And as you can see, everything gets its own. Comms is a little hard because I capacitated it just for a little bit because of how much, but we can figure that out later. But yeah, ignition is also a huge one, because in ignition we need a huge amount of power to start it. So that's probably also, we're gonna have to figure that out, but it's pretty straightforward. It goes from the generation to the SSU, which is basically for the battery bed into the main serial bus. And then so like you have the battery bed just powering everything. And then you have the main serial bus, and everything has its own SPDA. So there's two things you have to consider in these, which isn't that much. You have voltage regulation, and since latex sucked, I copied these from Wikipedia because there were pictures of them, so that's why that's there. But you have voltage regulation, where you have a voltage, just to calculate that, you have a voltage at no load, a voltage at full load, and then you divide that by the voltage at full load again, and then you multiply by 100. That should seem familiar, because that's the efficiency thing, or whatever that's called. And the way you have to worry about also is the power supply. So this is an open source power supply. It's a variable. So basically what it can do, instead of sending it all at one, this one can send it at different things. This is the one that's your computer. Your computer has this exact power supply. I mean, proprietary, because this one's open source, but, and there's a part list and everything online that I just didn't feel like putting on here. But this is basically what I'm going to base our power supply circuit for each thing off of, based off of what it needs. So moving forward, this is what I need for people, because these are all just feasibility studies. So there's no concrete system in place yet for power like there is for propulsion. So what we all need to do is we need to decide on one based off of our power needs, which propulsion and communications are going to be the biggest power needs. And then once that happens, I can just dive right into speccing equipment and stuff, because I'll be able to make load calculations, and that's really easy because all this electric stuff's already, we do it every day here. It's like our whole lives is run with power generation. We need to lay out a structure for the ship, because we need to calculate dumb things like head loss and stuff for the pipes, and just so we can spec all that out. So that's easy. And altogether, we need to move away from this schematic design phase and this feasibility, because we've been kind of stuck in this kind of, well, we could do this, or we could do that, we could do this, or we could do that. So it's becoming a huge problem, and we need to move away from that. So I'm hoping by next term, in the next 10 weeks, I'll be able to get straight up MATLAB code and some SolidWorks and some AutoCAD models, and we'll have schedules and stuff like that to figure out exactly what we need for the ship. Because none of this should be experimental. We should be able to have concrete calculations for power, because power is something that we do nowadays. That's it.
Can any of them feasibly get to, let's say, 1 gigawatt? Let's say if we could minimize down to 1 gigawatt.
Just make it faster. I mean, make it bigger. That's really the only thing you can do.
I know. Then we have mass issues. So we'll have to figure that out.
Basically, the only thing that we can do is generate the power on board. There's no way to distribute that much power without generating it there.
Okay, cool. I'm gonna see how much back power we can get from the propulsion system, and see how much we can reduce the load off of you guys. However, ignition we might be able to work off of the sun.
Oh yeah, yeah.
We
No,
can use
while we're
solar
in,
power for ignition, and then if we get enough power return.
while we're within, I think I had just using it was easy, like photon length, like wave packets and stuff. I think as far as we can go is I can still pull a decent amount of power at like Jupiter. I think you can still pull a decent amount of power from the sun, at least to charge the benzene, because you have it coming. Because the wavelength, the high wavelength or the low wavelength are still kind of high energy, so you don't really have to worry about that. But past Jupiter, we start having to use lasers as like some kind of like a loop.
Yeah, that's why I'm only thinking it would be, solar panels would only really be feasible if ignition is much higher.
Oh yeah, I hate the solar panel idea, but if we need it, because they're just so unreliable, and they only produce kilowatts of power at a time for the ISS.
Okay.
Yeah.